Okay, good afternoon. Boa tarde a todos. Posso falar? Speak in English? Okay. So today I have a pleasure to introduce you, Professor Jérôme Martin, our colleague and friend also. He was a graduate student in the University of Pierre-Marie Curie. He did a postdoc here in CBPF for 10 months. Stay here for 10 months. We did some work together with Ivano, right? Ivano Soares. And then now he is a researcher in Institut of Astrophysics de Paris, CNRS. He's always been investigating cosmology, inflation, and also the link of all that with quantum mechanics, how we can use cosmology and some particular features of the universe in order to have some information about quantum mechanics and vice versa. Okay? So it's a very interesting research, which I like very much. And then I think he'll try to show you how we can make this connection and what things we can obtain from this of these investigations. Okay, Jérôme?
So thank you very much for the nice introduction, and thank you very much for giving me the opportunity to present this colloquium. So indeed, as you can read on the screen, what I want to do this afternoon is to discuss the possibility of detecting quantum effects in the sky. And this possibility arises because, according to our understanding of the very early universe, all the structure that we see in the sky are of quantum mechanical origin, hence the possibility of seeing and detecting quantum effects on the celestial sphere. So in order to discuss this topic, I have organized the talk in the following way. So first of all, I will discuss the theory of cosmological perturbations of quantum mechanical origin during inflation, since this is the main tool that we will be using in order to discuss the main topic of this colloquium. Then in the third part, I will try to, in the light of the theory of cosmological perturbation, I will try to make some remarks about the main topic of the colloquium. And then in the fourth part, I will argue that we already have some proof, indirect proof, that the perturbations are indeed of quantum mechanical origin. And this proof is based on the recent measurement of the CMB anisotropy. And then in the last part, I will come to the main question, whether we can obtain in some way a direct proof of the origin of the perturbations. What do we need to do in order to have that, and what are the obstructions to this program? And at the end, I will present some conclusion. So, well, let me start by the theory of cosmological perturbations during inflation, and therefore let me start by telling you some words about inflation itself. So this will be quite quick. So inflation is a phase of accelerated expansion that took place in the very early universe, so prior to the epoch described by the hot Big Bang phase. This is here a sketchy representation of the timeline of the universe, and you see that inflation is supposed to have taken place just after the Big Bang and prior to the radiation and matter-dominated era that are described by the standard model of cosmology. So since it takes place in the early universe, it means that it takes place at very high energies. So the energy scale at which it takes place is not known, but we have a range of possible values for the energy scale of inflation. It should be larger than the highest scale that we have already probed, so maybe the BBN scale in the context of cosmology, or the scales that we have already probed at the LHC in Geneva. So it's not very precise, but let's say something like TV scale. And we know that it should be smaller than the gut scale, so 10 to the 15 or 10 to the 16 GeV. And therefore, this means that we have a range of possible value which span many orders of magnitude. And the inflation could have taken place anywhere in this range of values. Also, when you construct a concrete model, most models usually take place around the gut scale. So why do we like inflation? It's because it allows us to solve the puzzles of the standard model of cosmology. So inflation should not be viewed as an alternative to the hot Big Bang model, but rather as something which can complete the standard model of cosmology. And so nowadays it's viewed as a part of the standard model of cosmology, I should say. And how is it produced? Well, there are various ways of driving a phase of inflation, but let's say that the standard way is when there is a scalar field which dominates the matter content in the early universe, then you can show that it can drive a phase of inflation. So we don't know exactly the physical nature of this scalar field. It's named the inflaton field, the field responsible for inflation. There are some good candidates for the inflaton field, but we don't have any final conclusion regarding this physical nature of the inflaton field. So this means that during inflation, mainly two types of interaction or fields are relevant, the gravitational field and the inflaton field. And the two are coupled through the Einstein equation. But inflation is also interesting because it gives an explanation for the origin of the structure that we see in the universe. So the galaxies, the clusters of galaxies, the CMB anisotropies, and so on. And the idea is very simple and very drastic at the same time. According to inflation, the quantum fluctuations of the gravitational and inflaton field during inflation are amplified by the phenomenon of gravitational instability and stretched to very large distances, to astrophysical or cosmological distances, by the expansion of the universe. And so, and these fluctuations are the seeds of the structure that we see today. So if this explanation is correct, and by the way, I should mention in this institute that this scenario is also valid for some alternatives to inflation, like bouncing models, for instance. So if this explanation is correct, this means that everything we see in the sky are nothing but quantum fluctuations. So this is a drastic idea, beautiful idea, fascinating idea, but quite speculative idea. And therefore, the question is whether we can prove it observationally speaking. So this is one of the questions that I will be addressing during this talk. So this is the main idea. Let me show you some more technical aspects. Also, I will try to remain quite simple. So this is the idea. So I have this, I have space-time at the beginning of inflation, let's say, and roughly speaking, we know that it was homogeneous and isotropic. So the same in any direction, the same at any place. And on top of that, we have some very small fluctuations that are inhomogeneous. So that are like ripples on top of an expanding homogeneous and isotropic background. And so the idea is that the universe expands driven by this scalar field during inflation. And because of the expansion of the universe, because of the phenomenon of gravitational instability, the perturbation grow. And later on, subsequently, they give rise to the galaxies and to the CMB anisotropies. So how can we describe this simple idea in more technical terms? So what we do is that we remark that the perturbations are very small. We know that in the early universe, they were very small. And therefore, it's appropriate to use a perturbative approach to describe their behavior. So what we do is that we expand the two fields that are relevant in the early universe in this simple scenario, namely the gravitational field or the metric tensor and the inflaton field, and we expand them. The leading terms only depends on time, so they represent the homogeneous and isotropic background, and we add small fluctuations, so there is a delta here, just to remind you that these things are very small. They depend on space, so really they represent small inhomogeneities, and I have put a hat on top of them because they are quantum fluctuations. And for everything that I am going to say today, this expansion will be sufficient. So I will ignore the higher order terms and I will work with linear perturbation theory. And so you see that you have different type of different component of the perturbed metric tensor. You have the inflaton fluctuations, but in fact you can show that everything for the perturbations that we are interested in, that we see in the sky, can be reduced to the study of a single quantity. And this single quantity is either the curvature perturbation or equivalently the Mukhanov-Sasaki variable. So it's a scalar field, quantum scalar field, which is of course inhomogeneous. And physically speaking, you can think about this field as the amplitude of the small fluctuations that you have on top of this expanding background during inflation. So you can also, since we are considering linear perturbation theory, it's very often very convenient to go to Fourier space. So instead of working with the Mukhanov-Sasaki variable in real space, you can go also to Fourier space. And in that case, the fluctuations are just described by a collection of Fourier components, one for each wave number k or one for each wavelength. Okay, if we want now to understand and compute the behavior of those perturbations and to calculate their properties, we need some action for these perturbations. And in fact, here we don't need to postulate anything. The Hamiltonian can be obtained from first principle. So you just take the Hamiltonian of gravity, so Einstein-Hilbert action, plus the Hamiltonian of a scalar field, the inflaton field. You plug the perturbative expansion in this action. You expand everything to second order in the action, because when you vary this action, you want to obtain an equation of motion which is first order. And then you can, if you wish, from the second order action, apply the Legendre transformation to get some Lagrangian or some Hamiltonian. And if you just carry out this calculation, this is the Hamiltonian that you find. You find that your total Hamiltonian is a sum over all the modes of some Hamiltonian h of k. And this Hamiltonian h of k is given by this expression. So I'm going to discuss what it means physically. But you see that this Hamiltonian is quadratic, almost by definition, because I said that I had expanded the action at the quadratic level. So this is an Hamiltonian for each mode k, and the total Hamiltonian of the system is just the sum over all the modes for the system. So let me say a few words about this Hamiltonian. So this Hamiltonian resembles the Hamiltonian of an harmonic oscillator. P of k is the conjugate momentum to V of k. Roughly speaking, you see that this Hamiltonian is p squared plus q squared, the Hamiltonian of an oscillator. But there is a difference, is that the fundamental frequency of this oscillator is a time-dependent quantity. So in fact, we don't have to deal with harmonic oscillator or with a collection of harmonic oscillator, but we have to deal with a collection of parametric oscillators. So an harmonic oscillator would be like a pendulum, and a parametric oscillator would be like a pendulum, the length of which can change with time. And why we have this in this context is very simple. We know from elementary consideration in QFT that a field is just an infinite collection of harmonic oscillators. Here we have a field, but this field lives in a time-dependent background, the expanding space-time. So our Mukhanov-Sasaki variable, our quantum field, is just a collection of parametric oscillators because the fact that it lives in a dynamical background gives to each fundamental frequency for each oscillator a time dependence. And this time dependence is, of course, controlled by the dynamics of the background. So in other words, for different expanding background, you would obtain different time dependence for the fundamental frequency of the oscillator that make the field. So the inflationary mechanism for structure formation may seem at first sight as something which is quite speculative. After all, we are talking about the early universe. Very high energies could be as high as the gut scale. But in fact, from the point of view of quantum field theory, it's something which is quite standard, and I would even say conservative. In fact, this mechanism is akin to well-known other mechanisms in quantum field theory, such as the Schwinger effect or the dynamical Casimir effect, which has been seen in the lab. So each time you have a quantum field which is interacting with a classical source, you have this type of phenomenon. So this is the case for the Schwinger effect. For instance, you have a fermions interacting with a classical electric field. Here we have this small quantum fluctuation, and they are interacting with the classical gravitational field, which represents the dynamics of the background. So it does not come as a surprise that this phenomenon belongs to this class of effects. Now there is a small technical twist that I would like to introduce for the following. And this is the following. So the Mukhanov-Sasaki variable is not a very convenient variable for what I would like to do because it is a complex variable. The Mukhanov-Sasaki field in real space is real, and therefore it takes 2 lines of calculation to show that its Fourier component should satisfy this relation. So this means that this operator is not an Hermitian operator, and moreover, this means that it mixes mod k and minus k. And it would be more convenient to have a quantity which represents the amplitude of the signal at a fixed scale k without mixing k and minus k. And so in the following, I will rather work in terms of the quantity q of k and pi of k, which is its conjugate momentum, which, as you can see, if you look at the expression in terms of creation and annihilation operator, does not mix mod k and minus k. So q of k is really like the amplitude of the oscillator that you would obtain when you study the harmonic oscillator in some basic textbooks on quantum physics. So the amplitude of at a fixed scale will be represented by the operator q of k. And if you now express the Hamiltonian of the system in terms of this new variable, well, you still find a sum over all the oscillators that you have in the system. But now the sum is over h of k, which is the Hamiltonian for mod k, plus h of minus k, which is the Hamiltonian for mod minus k, which would look like the same, plus a term which is like an interaction term between mod k and minus k, and which looks like this. So mod k and minus k in this context are not independent, and in some sense they interact. So of course they interact in some sense linearly because the Hamiltonian has to be quadratic by definition. And you also see that if I am in a situation where the fundamental frequency of the oscillator does not depend on time, then omega square would be k square in that case. And you see that this interaction would vanish. This interaction Hamiltonian would vanish. So it's really the fact that my field is living in a dynamical background, in an expanding space-time, which is responsible for the presence of this interaction term. And well, now I have everything. If I want to calculate the evolution of the system, the only thing I have to do is to solve the Schrödinger equation, which is given here, where H is, of course, the Hamiltonian that I have discussed in the previous slides. So remember that we are doing linear perturbation theory. So this means that I can always write the total wave function, or I should say wave functional, as an infinite product of a wave function for mod k and minus k. And if I plug this decomposition, if you wish, into the full Schrödinger equation, I obtain a Schrödinger equation for each wave function for mod k and minus k. And then the question is, the only question which remains is to solve this equation. And if I want to solve this equation, the first thing that I need is some initial conditions for the wave function. And here comes one of the assumptions for the inflationary mechanism. The assumption is that we start from the vacuum state. So all these oscillators are initially placed in their vacuum state. And once I have these initial conditions, the only thing I need to do is to integrate the Schrödinger equation to find the unitary evolution of the wave function starting from this initial state. And what I find is that, so it's given by an expression like that, where the wave function is a Gaussian state. And again, it does not come as a surprise. I have an Hamiltonian which is quadratic in the position and momentum. Therefore, the only thing I can find when I solve the Schrödinger equation is a state which is a Gaussian state. So let me try to say something more about this Gaussian state. First, the initial state. So the initial state is the vacuum state, as I said. Vacuum state for mod Q of k and Q of minus k. So, well, the ground state of an harmonic oscillator, of an oscillator, is exponential minus Q square, or minus x square over 2, if you wish to use the position as we are used to. And so this means that the ground state of my system is just given by the product of two Gaussian states. And if I write it in terms of the combination Q of k minus Q of minus k and Q of k plus Q of minus k, I obtain something like that. So it's just a Gaussian state, which is rotationally invariant in the space Q of k, Q of minus k. And if I look at the wave function in this space Q of k, Q of minus k from above, what I see is just a circle. Hence this. So this is my initial conditions, and then I have to calculate using the Schrödinger equation the evolution operator of the system. And in that case, the evolution of the system is such that I evolve the system into a two-mode squeeze state, which is a well-known state in other branches of physics, for instance, quantum optics. So let me just try to discuss a little bit more the two-mode squeeze state that we have in cosmology. So first of all, you see now that it depends on this function R of t, which appears when I integrate the Schrödinger equation, which means that now the combination qk minus q minus k and qk plus q minus k, in some sense, do no longer carry the same weight. So this means that when I represent the wave function in the space qk, q of minus k, I no longer have something which is rotationally invariant, but when I look at the wave function from above, I see an ellipse, hence the name of the state. You see that the initial circle has been squeezed, hence the name of the squeeze state. And this function R of t, of course, depends on the dynamics of the background. Therefore, it depends on the scale factor during inflation. And the important point is that this function R of t only depends on the background, and during inflation, it grows. It grows a lot, in fact. And in fact, if you take the logarithm of this function, this is the well-known squeezing parameter that people usually discuss in other branches of physics. And by the way, it's interesting also to comment on the numerical value of the squeezing parameter at the end of inflation. Because the cosmological two-mode squeeze state is in fact turns out to be a really the strongest squeeze state, I think, ever considered in physics, in nature. In fact, if I am not mistaken, the world record for the squeezing parameter in the lab is something like 15 decibel, while in cosmology, at the end of inflation, we estimate the value of the squeezing parameter to be larger than 500 decibel. So the cosmological two-mode squeeze state is the strongest squeeze state ever observed in nature, which makes cosmology an interesting area to discuss this type of physics. Okay, so this almost conclude my first part of the talk. We have, so these quantum perturbations are placed in this strong squeeze state at the end of inflation. Then the universe continues to evolve, and these quantum perturbations are the seeds who give rise to the CNRS anisotropies and then to the galaxies. Here we have inflation, so time is going like that. We have inflation, we have those quantum fluctuations that I have described, and then they give rise to the temperature anisotropies that we have detected with various missions, and later on, they give rise to clusters of galaxies and galaxies. So this is the main idea. So now let me, in the light of what I have just explained, let me try to ask the main question again. So here I just repeat what I have said. So according to this theory of inflation, so all the structures, CMB anisotropies and galaxies, are nothing but the quantum fluctuation of those fields, amplified during inflation and stretched to very, very large distances and placed in a strongly squeezed state. So this is interesting because it's an example which shows that quantum mechanics operates not only on small scale, how we are used to, so useful formalism to describe I don't know, elementary particle physics, atomic physics, molecular physics, condensed matter, and so on. But here we have an example where, if inflation is correct, where quantum mechanics operates in the sky and on very large distances. So this is interesting, I think. And this is also interesting because I think that inflation, or the early universe, if you prefer, I think is the only situation in physics where you need general relativity and quantum mechanics to derive the predictions of a theory, and where at the same time you have high accuracy data from the CMB, for instance. I don't know any other example in physics so far. It's also interesting because the inflationary mechanism is related to quantum gravity, clearly. So it's not we have to be modest here. It's of course not full quantum gravity. We don't have to face questions like renormalization, regularization. We don't need string theory or any other, your favorite theory of quantum gravity, loop quantum gravity or something else. Here, we don't need that to treat this question. But clearly, this has something to do with quantum gravity in the sense that I have put a hat on delta G mu nu at the beginning. So this is also interesting. So given all these remarks, the question is, can we prove that this is indeed something which works and which is in agreement with the observations? So this is now the next section. So now I am going to argue that we already have an observational proof that this mechanism is correct. So this is what I would describe as some indirect proof of the quantum origin of the perturbation. And this is based on our measurements of the CMB anisotropy. So let me explain a little bit. So here you see the map of the CMB anisotropy obtained by the European Space Agency satellite Planck. So you see that you have different temperature in different direction. The typical amplitude of the variation is 10 to the minus 5. So indeed, the perturbations are small. So our perturbative approach is valid. Well, in order to calculate or to understand the properties of the CMB anisotropy, to calculate, for instance, the statistical property of the CMB fluctuation, it's convenient to Fourier transform the signal, but here the signal lives on the celestial sphere. So it does not live in 3 dimensions. So in order to Fourier transform a signal on a sphere, what we have to do is to expand it in terms of spherical harmonics, instead of plane waves. And the coefficient of the expansion, the ALM, are just the Fourier component of the signal on the sphere. And then to calculate the statistical properties of the signal, what we do is that we calculate the average of the square of the Fourier amplitude, which is known as the power spectrum. So this is, which in cosmology is named the multiple moments. So the multiple moments are just the Fourier, the power spectrum, if you wish, of my CMB fluctuations. And these multiple moments, they depend basically on 2 things. They depend on what was happening during inflation, because the perturbations that I have described were the seeds of those fluctuations. So different behavior for the perturbations during inflation would lead to different multiple moments. And of course, they also depend on the physics after inflation, which is described by the usual cosmological parameters, such that the Hubble parameter, the amount of radiation of dark matter, and so on. But we believe that we understand the physics after inflation. It's just the hot Big Bang model, which works very well. So, in fact, it depends on the statistical, so the power spectrum of the CMB fluctuation essentially depends on the power spectrum of the fluctuations during inflation. The power spectrum is just the 2-point correlation function of the Mukhanov-Sasaki variable in Fourier space. And therefore, by observing the multiple moments that you extract from this map, you can say something about the power spectrum of the fluctuation during inflation, and therefore you can check whether your theory of perturbations is correct or not, because this quantity, you can also compute it using the consideration that I have shown before. And in fact, a generic prediction of the formalism that I have presented before is that the power spectrum should be given by this power law, where NS is known as the spectral index, and the general prediction generic prediction of inflation is that NS should be close to 1. So NS being exactly 1 would be what is known as a scale invariant power spectrum. So a power spectrum which does not depend on the scale at which you consider the signal. But the prediction of inflation is that the power spectrum should be close to that, but not exactly that. And therefore, that NS should be close to 1, but not exactly 1. So this is the generic prediction of inflation. So how close to 1 it is depends on your model of inflation. So it depends on the precise form of the expansions during inflation. But for all types of inflationary model, NS should be not 1, but close to 1. And using the CMB data from Planck, we can extract the power spectrum of the CMB fluctuation. So this corresponds to the blue dots in this graph. And from that, you can use some data analysis machinery and extract the value of the spectral index. And what you find is that NS is 0.96. So in perfect agreement with what inflation is telling you. And with the Planck data, this is the first time that we have a statistically significant measurement of the deviation of NS from 1. So we know that NS is not exactly 1 at more than 5 or 8 sigmas now. And this is the first time that it has been obtained using CMB data, thanks to the Planck satellite. And therefore, these predictions of inflation, and here I stress that it is a prediction of inflation, namely that this prediction was made before this measurement was carried out, has been confirmed by the Planck satellite, and therefore this constitutes an indirect proof that the perturbations indeed obeys the properties that I have described before, and that are indeed of quantum mechanical origin. So I would say, if you postulate that what we see in the sky are just quantum fluctuation, you can infer predictions that match the data. So quite interesting, but maybe not sufficient. Now let's try to obtain something. Let's try to be more ambitious, and let's try to obtain a direct proof of that the perturbations are quantum. How could we proceed? And is it possible in principle? And is it possible in practice? So there is a standard argument in the field of cosmology which claims that, in fact, it's not possible to obtain a direct proof of the quantum origin of the structure that we see in our universe. And the argument goes as follows. You can show, and I will comment a little bit on this property, that in fact all the quantum correlation function that you can calculate using the quantum correlation function of the perturbations that you can calculate, you can show that you can reproduce them using simply a classical stochastic process. So based on this property, people usually argue that there is no quantumness with quotation mark left in the system, that the quantum to classical transition has been achieved, and that it's impossible to see any hint of the origin of the perturbation. So in the literature, this is known, also I think it's a very bad expression, it is known as decoherence without decoherence. Also, this has nothing to do, in fact, with decoherence, but so let me explain mainly what people have in mind. So, in fact, the following is true. If you calculate, let's say, the mean value of the operator Q of k squared. So this is, roughly speaking, the power spectrum. I take the amplitude of the signal, Q of k, I square it, and I take the mean value of it. So this is the power spectrum. So something that I observe, the quantity which I was mentioning before and which is almost scale invariant. So by definition, this is the trace of this operator times the density matrix of the system. But there is a theorem. So here we are talking mathematics. There is nothing physical here, that you can always express this quantity as an integral over classical phase space. So over Q of k and pi of k, but there is no hat now. They are classical variable in phase space of the corresponding quantity, qk squared, but without a hat, times a function which plays the role of a probability density function. And this probability density function is in fact known as the Wigner function of the system. And this is, in a sloppy way, this is the Fourier transform of the density matrix in position representation, in a sloppy way. And this is always true. There is no physics here. This is just a mathematical identity. So the quantum correlation function of Q of k squared is always, according to this equation, equal to the stochastic average of the corresponding classical counterpart. And again, I emphasize that this is exact. This is a mathematical identity. But of course, for this expression to make sense physically, there is a condition, is that the probability density function should be positive definite. Because otherwise, I have this expression which is indeed correct mathematically, but physically this would be meaningless. And it's not always true, of course, that the Wigner function is positive definite. Let me just give you an illustration. So let's take the Wigner function of a Schrödinger cat. So you have a particle which is here in superposition with a particle there. You calculate the Wigner function. What you find is a bump which corresponds to the first location, another bump which corresponds to the other location, and in between you have oscillations, because of course you have interference between the two branches of the wave function. And because of this interference, you see that the Wigner function can be negative. So in that case, nobody would argue that, in the case of the Schrödinger cat, nobody would argue that the situation can be described classically, because in some sense, this is an expression that sometimes you find, this would involve negative probability. But now let's consider our system again. We know that the quantum state of the perturbation is a Gaussian state. It's a two-mode squeeze state, which is a Gaussian state. The Wigner function, I said, is basically the Fourier transform of the state of the system. So the Fourier transform of a Gaussian is a Gaussian. Therefore, the Wigner function of my system is a Gaussian state. And therefore, it's positive definite. This is a representation of the evolution of the Wigner function during inflation. So it starts with a Gaussian bump, which corresponds to the coherent state, so the initial state, the vacuum state, and then you see by eyes the squeezing of the state as the universe expands and as inflation proceeds. So since the Wigner function is a Gaussian state, this means that the corresponding PDF is positive definite, and therefore, hence the origin of the claim that any correlation function in the system can be, in a meaningful way, reproduced by a classical stochastic process. Hence, therefore, the claim that any quantum signature in the system would have been completely erased. This is the origin of this claim. Now let's try to think about this claim a little bit more. If you think about it, nevertheless, it seems a bit strange. And it is strange for instance, because of that, because we have seen that the wave function of the two mode squeeze state, so for mode k and minus k, cannot be put under the form of a product of a wave function for mode k times a wave function for mode minus k. So this means that this wave function is in fact correspond in fact to an entangled state. An entanglement, nobody would dare to describe it as a classical situation. So this means also that there should be some quantum correlation in the sky. So some correlation in the sky, in the Planck map, according to this, that could not be understood in a classical fashion. This state is also a discordant state. The two-mode squeeze state is a discordant state. So if you calculate the quantum discord, which is a criterion which allows you to decide whether you deal with a classical or a quantum situation, for this two-mode squeeze state, you obtain this plot. So this is quantum discord versus the squeezing of the state. So initially, your quantum discord vanishes. It makes sense because initially we have a coherent state. A coherent state is the most classical state that we can have. So the quantum discord is zero in that case. But as soon as R is not zero, the quantum discord is not zero, and therefore, according to this criterion, which comes from quantum information theory, there should be some quantum correlation in the system. In fact, you can show that for a quite large value of R, these scale linearly with the squeezing parameter. So not only our scale is entangled, but it's also discordant. Well, maybe the two are the same in this particular case. But clearly, this indicates that, at least at first sight, it's not a situation that I can describe classically. So here, the situation seems to be a bit paradoxical. Using some argument, I come to the conclusion that the system is classical, and using other arguments, I come to the opposite conclusion, namely that no, it should be quantum. So how can we understand this situation? So it seems that despite this argument of decoherence without decoherence, there is some quantumness that remain in the system. And the question is, where is it hidden? And can we observe it? Because if I can observe it, this would be a direct proof of the origin of the perturbation. And so how can I do this? Well, a standard way is to take a system and try to reveal or highlight correlations that I cannot explain classically. This is typically the case of the Bell experiment that was performed by Alain Aspect. What you have correlation between Alice and Bob, and you have some correlation between Alice and Bob that you cannot explain classically, and therefore you know that there is something quantum in the system. So one possibility, this is just one illustration that I would like to present at the end of this talk, is one idea would be, can we build a cosmological Bell experiment? Is there a way to mimic what is done when people measure the violation of the Bell inequality? Is there a way to do it in cosmology? So this is what I'm going to explain in 5 minutes at the end of this colloquium. But before that, I would like to make some historical aside and some propaganda. In fact, this question is a question that has already been considered elsewhere in physics. People have already wondered whether a system which has a positive definite Wigner function can at the same time violate some Bell inequality. And in fact, the first guy who wondered about this question was John Bell himself. And you know this famous book by John Bell, Speakable and Unspeakable in Quantum Mechanics. If you go to chapter 21, this chapter is entitled EPR correlation and EPW distribution. So EPR correlation, it means correlation between violation of his own inequality, of the Bell inequality. You know that the paper of Bell was based on the EPR paper. So this is what he means here. And EPW distribution means Eugen-Paul-Wigner distribution. In other words, the Wigner function. And by the way, this paper is dedicated to Professor Wigner. And in this paper, Bell asks exactly the same question that I am asking, and that is relevant for cosmology. Also, this was done before inflation. Of course, John Bell was not aware of what inflation is, and probably did not care about inflation at that time. But nevertheless, he had this question in mind, whether a system which has a positive Wigner function can or cannot violate or exhibit some non-classical correlations. So now comes the propaganda part. If you are interested in this history, I have written a paper on that where you can, you can follow the history, because this seminal paper by Bell was followed by many others. And we know now, this is, you know that, for instance, Albert Einstein has written some wrong paper on general relativity. It's very well known. And here, if you follow this story, you will discover that John Bell has written some incorrect paper on quantum mechanics, and you can follow the history in my historical paper if you are interested in. Okay, so now let me finish with this idea of trying to have a cosmological Bell experiment to reveal the quantum origin of the perturbations and to see some quantum effects in the sky. So I just remind you very briefly about the Bell experiment. So the aspect experiment. So here we have a source which emits two particles, two spin 1/2 particles that travels in opposite direction. And at position A, you have Alice with some polarizer, which is measuring the spin of the particles. And on the other side, you have Bob. And Bob has also a polarizer and measure the spin of the particle that he detects. The quantum state of the system is the Bell state. So this is an entangled state. And this is the reason why there are something non-classical going on in the system. And you know that Bell was able to introduce a quantity which we now describe as the Bell operator, which is a combination of the value of the spin at Alice and Bob's location. So you can, UA and UB are the orientation of the polarizer at Alice and Bob location. And you can choose the polarizer's orientation in an optimal way. So, it's just a technical detail, but if you calculate the mean value of this quantity introduced by Bell, we know that classically this quantity has to be less than 2, and quantum mechanically it can be larger than 2. And you know that Alain Aspect has observed values of B that are at a very statistically significant level, larger than 2, so beyond the classical limit. And therefore, this is how we know that we have quantum correlations in that system. So this is the simple reminder of the Bell experiment. So can we do the same with cosmology now? Well, we need a bipartite system. And clearly in our case, the two particles will correspond to mod plus K and minus K. We need some spin operators. So here comes something that I wish I had more time to explain, but you can define what is known as pseudo-spin operators. So these are these complicated operators. You know that they are expressed in terms of the eigen vector of the Q of K operator. And you can show that these pseudo-spin operators are spins, in the sense that the square of them is always the identity, and the three components obey some SU2 commutation relation. So they are really spin operators. And so they only depend on the well, they can be expressed in terms of the eigenvector of Q of K, hence the hope that if you measure Q of K, maybe you can infer observationally the value of these pseudo-spin operators. What would be the equivalent of the Bell state? Well, clearly the two-mode squeeze state, which is an entangled state. And the Bell operator, well, you just mimic the expression that was defined by John Bell. Of course, in this situation, I must confess that I have no clear analogy for what would be the orientation of the two polarizers. But after all, this is not so important. You can always choose them in such a way that they are optimized in the way optimized to violate the classical limit. Also, it's not very clear to me how, I don't have any image of what would be the polarizer orientation in that case, but again, I repeat, you can always choose them in an optimized way. And using all that, in fact, you have everything you need to construct a cosmological Bell experiment and calculate the mean value of the Bell operator in that case. And well, this has been done. And here is the answer. So this is mean value of the Bell operator in the two-mode squeeze state as a function of the squeezing parameter. The classical limit is 2. So for the pseudo-spin operators that I have considered, you should look at the dashed lines. And you see that the dashed lines, so they depend on so there is another squeezing parameter in the here, which is the squeezing angle. So, but it's not important. What you see is that depending on the value of the squeezing angle, the value of B is always larger than 2. And therefore, you violate the Bell inequality exactly as the Bell inequality is violated in the usual aspect experiments. So in principle, this proves if we could measure this pseudo-spin operator, we would be able to prove that there are correlations in the Planck map that cannot be understood in classical terms. Unfortunately, life is not so easy, and there are some obstructions to this program. And now, this is my last slide. I'm going to describe what are the obstructions. So first obstruction, we know that the Bell inequality is violated because we know that classically B cannot be greater than 2. And why cannot it be greater than 2? It's because in the standard situation of the Bell inequality, we have the locality assumption. It's because probability of something which has to deal with Alice and Bob can be factorized as the probability of any property relevant to Alice times the probability any property relevant to Bob, that we can prove that classically B must be smaller than 2. But here we are doing the Bell inequality in Fourier space. And in Fourier space, there is no notion of locality. So there is a priori no reason to postulate that classically the joint probability of Sk and S minus k can be factorized. But if I lose this property, I can no longer prove that classically P must be less than 2. So if I find something which is larger than 2, this does not mean that there is some quantum correlation in the game. So what this tells me is that I should not work in Fourier space. I should do it in real space. So I should really take the Planck map and study the correlation, not in Fourier space, but in real space. But the problem is that if you do this, and this is something that we have done, you find out that the quantum discord, which was very big in Fourier space, is now completely damped in real space. And as a result, the Bell inequality violation disappears. So this idea of observing this correlation fails for this reason. In fact, there is another reason why it fails. This is obstruction 2. We know that the Bell inequality violation requires at least the measurement of 2 non-commuting quantities. So, for instance, 2 components of the speed. But so in cosmology, one quantity that we can measure is the amplitude Q of k, the amplitude of the signal at a given k. But we need another quantity. And this quantity can only be the momentum. But in perturbation theory, in fact, the momentum in a cosmological context cannot be measured in practice because it is associated with the decaying mode and it is exponentially suppressed. So probably this decaying mode is out of reach forever. It's really strongly exponentially suppressed. So this is another obstruction. And it fails for this reason as well. Okay, so let me now just present some conclusion and then I will close. So the first thing is that we have evidence that quantum mechanics not only operates in the micro world, but also in the sky. If you make this strong assumption, the consequences that you can infer from them seem to match the data. So this is clearly correct. But of course, we would like to be more ambitious and try to observationally and directly reveal those quantum aspects. And so far, no direct proof is available. Nobody has been able to find a test or a strategy, a tactic to reveal or highlight the quantum origin of the perturbation beyond just noticing that they match the CMB data. So a first attempt, which was based on this Bell experiment ID, so trying to highlight correlations in the sky that cannot be described classically, fails. And of course, the question is whether the obstructions that I have sketched before, are they really generic to any attempt that would try to reveal those correlations, or are they peculiar to the fact that I have tried to mimic the Bell experiment? To my knowledge, this is not known. Maybe after all, each time, maybe they are generic, this obstruction, and in that case, this would mean that there is a kind of cosmic quantum censorship theorem, namely that the origin of the perturbation is hidden to us and forever. And the takeaway message is that inflation and alternatives to inflation, physics of the early universe, so is not only an interesting or are not only interesting scenarios to try to understand and describe the physical conditions that prevailed in the very early universe, but they are also useful and fun and interesting playgrounds to discuss some foundational aspects of quantum mechanics. And with this takeaway message, thank you for your invitation. I stop here.
Thank you, Jérôme, for your wonderful talk. Okay. Questions?
Thank you very much, Professor, for this talk. My question is, you said that you constructed correlations that cannot be described classically, right? And you are saying that because the Wigner function becomes negative? What do you mean?
No, I said that you can construct correlation function that can be reproduced exactly by means of a classical process. And the reason for that, so this is always true mathematically, but this is physically meaningful because indeed the Wigner function is, in that case, in the case of cosmological perturbation, is positive definite. Therefore, you can always interpret it as a CBF, as a probability density function, a Gaussian one. So
Yeah.
in other words, if you postulate that the fluctuations in the CMB are just given by a Gaussian stochastic process, you can calculate and reproduce without any problem the correlation function that we observe.
Okay, so you're saying that the correlation that you constructed satisfies these, but should be somehow non-local. So that's
Why non-local?
yeah. And I don't understand because you said you constructed correlations that satisfies these,
So,
right? But are
so
quantum.
this equation is always true.
Yeah.
You can always, if you want, you can always view any quantum correlation function as a classical stochastic correlation function. The point is that it is, because this is a mathematical identity.
Yeah.
So but physically, it is meaningful only if what you interpret as the probability density function is positive definite, which is not always the case, but
Yeah,
which is the case for perturbation.
Yeah, so what I'm asking is, so how do you evade this when you construct the correlation?
Okay. So this is a good question. So you mean for the Bell experiment?
Yes.
Yes. Good question. So in fact, this is so I told you that the situation was a bit paradoxical because if you follow this line of argument, the perturbations are classical. But if you notice the fact that the state is entangled, it seems to be quantum. So how I can make these two things compatible?
Yeah.
Yeah. And John Bell has been wrong about this. In fact, the situation is interesting from the historical point of view. The situation has been clarified only quite recently, 2010, I believe. And in fact, this equation is, this equation is in fact, is just a particular case of a more general equation. In fact, instead of qk square here, I should have if you want, the Wigner function associated to this operator, which is known as the Weil transform of an operator.
Mm-hmm.
So it turns out that the Weil transform of q square is q square. And this is why I have written q square here. But this is not true for all operators. And in particular, this is not true for this pseudo-spins operator that I have shown. So in fact, this equation for a pseudo-spin operator, as it is written here, is not correct. If I write the Weil transform of the spin operator, it is correct. But the Weil transform of the spin operator is not the spin operator. I don't know if you understand what I mean.
Yeah, I think I understand.
So for the spin operator, if you wish, this would not be W times S squared. Because here they should stand the Weil transform of S squared. And the Weil transform of S squared is not S squared. But the Weil transform of Q squared is Q squared. And this is the reason why I have written Q squared here. And so, in fact, I asked the question in the situation where you have a positive definite Wigner function and an entangled state, there should remain some quantumness in the system. Where is it hidden? In fact, it's hidden in the correlation function of the operators that have a non-trivial Weil transform, which is not the case of the power spectrum, but which is the case of this pseudo-spin operator. This is what has been established by in 2010.
Thank you.
So thank you, Jérôme, for the nice talk. Is this idea of the quantum fluctuations capable to explain the Byron asymmetry in the universe? I mean, you said, you said that the main idea is, if I understood correctly, is that everything we see comes from quantum perturbations. But what about what we don't see, which is the antimatter?
So I'm not an expert of baryon asymmetry, but I would say no, it cannot explain this, because you need some specific interaction which violates some quantum numbers. So in this inflationary scenario, usually matter is produced at the end of inflation during the phase of what is known as reheating. And so, no, I don't see the connection between those fluctuations and the problem that you mentioned. But I am not an expert at all of baryon asymmetry. But, I don't think that in this simple formalism you can solve this problem.
Hi, thank you for your talk. Just a small comment. These measurements of Bayer inequalities, violation of Bayer inequalities with two-mode discrete states have been performed, I mean, many places, even here in Rio. It's the Federal University and also the Federal University of Fluminense and also in the region. So my question is, so you said that Bayer inequalities would be very hard for you to measure the kind of the non-commuting observables, but there are some other strategies to detect entanglement, which are entanglement weaknesses, right? So there's this criteria by Du and other people, I don't remember the names now, where you have to measure the variance of, well, you still have two observables, but you just have to measure the variance of them. And this has to satisfy some inequality. So if it violates, then you do have some entanglement. So I wonder whether this could be of any use in your case. I mean, do you have access to other observables, or just you can only measure these?
No, you can. So yeah, if you need two observables, the problem in cosmology is that you don't have access to two observables. So, but in fact, I know maybe a way out. Maybe you are also, you know, also this. Also, this has not been completely worked out, but we are working on it at the moment. So as I said, the limitation in cosmology is that we only have access to, let's say, the position and not the momentum, because the momentum is completely exponentially suppressed. So I think this is one of the reasons why this strategy with Bell inequality cannot work. So we have to think about a situation where I could highlight some quantum aspect by measuring only one quantity. And I think there is such a situation which would consist in measuring this quantity, but at different times. So at different redshift. So this is the Leggett-Gark inequality. So this is the path that we are exploring at the moment to try to shortcut this problem that we don't have access to the momentum. So, but this would require observationally to measure the power spectrum at different redshift, but there are some missions such that the Euclid satellite that precisely aim at doing that. So we are trying to explore whether the Leggett-Gark inequality could be a way out of the obstructions that I have listed before.
Yeah, I'm no experimentalist on that, but if I'm not mistaken, the way you measure in the lab, you have to measure the quadrature X, so to say, and to measure P, what you actually do is just kind of, you go from the near field to the far field. So to some extent, it's what you're saying, like measuring different times, right? So you just let light evoke, and then it changes by a Fourier transformation, right? Like free light just makes the Fourier transformation. So maybe that's really what you're saying. Thank
you. When you say measuring entanglement effects, this is something that is imprinted back there in the primordial universe and is like kept frozen, or is it something that keeps entangled no matter what? Because the same argument that says that quantum fluctuations decohere to become classical would serve to make any entanglements at the beginning of the universe to disentanglement, like the gravitational backgrounds, whatever. So if there is entanglement, it would be washed out by expansion, unless some signature remains frozen from the beginning. So my question is, this kind of thing that you're thinking of is about entanglement that's forever holds, or is assuming that something got imprinted there?
No, you are totally right. It could have been obstruction number 3. Because decoherence is going to hit you very hard. And in fact, we have done, so I did not have time to show it, but we have done some calculation of decoherence, assuming that you can measure this Bell inequality, something that you cannot do, but just to. And of course, decoherence has the tendency to wash, as you said, to wash out the violation of the Bell inequality as expected. But then, of course, the amplitude of the effect, in fact, depends on the strength of the interaction between the system and the environment, something that you don't know. So for some values of this interaction rate or interaction coupling constant, the effect is completely washed out. And for other values, it remains a little bit of violation of the Bell inequality. In fact, there is another calculation that we have done is to try to consider the environment as being the non-linearities of those perturbations, because we know that those terms are present anyway. And if you do this, so you find that, first of all, this is a complicated calculation, so you have to write a Lindblad equation, and it's not at all trivial. You meet many difficulties. But at the end of the day, what you find is that probably decoherence will wash out anything which has spent semifolds outside the bubble radius during inflation. But on much smaller scales, some quantumness could remain. So there is a good news is that some quantumness could remain in the system. The bad news is that, observationally speaking, it's very difficult to have access to these very small modes. So I'm talking about modes that exit the Hubble radius a few e-folds before the end of inflation. So today they would correspond really to very small scale, and we don't know exactly how to probe them.
Yes, so thank you for a very nice talk. But I have a question, maybe a naive question. When you speak about measurements, which measurements do you refer? And which are the equipment you are using?
So a quick answer would be, please attend my seminar tomorrow. Because this is exactly the topic that I will try to cover tomorrow. So of course, I am using quantum mechanics. So there is the quantum measurement problem. I have not said anything about the quantum measurement problem here. So, but there is this problem, yes. But for measurement, I was just mentioning the CMB measurements. So, well, it's a complicated question. It would be very long to answer it, but I will try to discuss this tomorrow. But yeah, there is the measurement problem here. So to tell you in a non-politically correct way, the truth is that in principle, when you perform a measurement on this system, the system of cosmological perturbation, you should reduce or collapse the wave function, right? But it's very hard to believe that just because me on Earth, I am looking at the very early universe, I am responsible for the collapse of the wave function. Power. Yeah, the power, absolutely. Yes. So there is this quantum measurement problem here. And what people have tried to do is just to consider alternatives to the standard formulation of quantum mechanics to deal with that problem. But this is not an easy problem in this context. I agree.
So thank you for the nice talk. And I also have a kind of maybe naive or stupid question is related to the it's because I mean you are building your whole I mean the foundation of the observables that you are trying to match using linear perturbation. So you are using perturbation theory, and then we get the result that actually in the CMB at CMB scales, for example, these large scales, we can't extract much information, but we need to maybe look to another, go to non-linear, go to a different approach to using something, for example, in order to compute the Paul spectrum, you are assuming somehow that your curvature perturbation zeta is, or the Muhanov-Sazak is much less than 1, right? Is this, so you are working this limit. So maybe if we go to different limits,
yes, so, well, first of all, it's well justified because delta t over t is 10 to the minus 5.
Yeah, but
you are right that maybe the question that you are asking is that of non-Gaussianity. So if you just consider the next two leading order terms. So of course, this is also maybe an interesting topic, namely trying to find some quantum signature of the perturbations in the non-Gaussianities. So just to give you one idea, there is a theorem which states that the only quantum state for which the Wigner function is positive definite are Gaussian states. So if you now go to the next two leading order and takes into account cubic term in the Hamiltonian, it's clear that when you solve the Schrödinger equation, the state will no longer be a Gaussian state. And therefore, you are guaranteed that the corresponding Wigner function will be negative somewhere in classical space. And this would be a place to look for some quantum effects. So I agree, if this is your question, I agree with you that trying to investigate the non-Gaussianities in this context is an interesting question.
okay, thanks.
Okay, so no more questions? Okay. So let's thank again, Jérôme.
Jérôme.